Why do 90% of students just throw away an entire grade boundary on the very first calculation of their Cambridge IGCSE Physics exam? It's the ultimate unforced error, and honestly, it happens every single year. Let's get right into it.
You know, when you sit down for that 0625 exam, it's kind of like walking into a vault. Are you legally stealing the examiner's marks, or are you just handing them right back? Because here is the harsh reality. A brilliant, perfectly executed math calculation in physics, it means absolutely nothing if your units are missing or your significant figures are completely butchered. So in today's explainer, we're basically staging a mark scheme heist. We're going to decode exactly how to secure those points together.
To really understand how the examiner thinks, we've got to ground this in reality. Think about pilots on a flight deck. For them, measurement is literal survival, right? A measurement error in basic quantities up there isn't just a lost mark on a test, it's a complete disaster. Those instruments give the crew critical info about the aircraft, and they rely entirely on accurate numbers and standardized units. Well, guess what? The examiner looks at your exam paper with that exact same demand for precision. If your numbers don't have the right context, they crash.
All right, let's dive into this by grabbing the fundamental tools for our heist. Before you can measure anything, you need a standard unit. These are the three foundational physical quantities that the whole SI metric system is built upon. We've got length measured in meters, mass in kilograms, and time in seconds. Literally every other mechanical unit, like newtons for force or joules for energy, is just some combination of these three. If you drop these basics, the entire foundation just crumbles, taking all those easy marks right along with it.
And this brilliantly illustrates our next tool, powers of 10 shorthand. Physics deals with the incredibly massive, like the mass of a literal star, and the incredibly tiny, like the width of an atom. So instead of rating out a massive string of trailing zeros, which, let's be real, is just begging for a transcription error, we use standard form. 4,000 becomes 4 times 10 to the power of 3. 0.04 becomes 4 times 10 to the negative 2. This is the exact language the examiner expects you to use. It's a really neat, precise way of showing you actually understand the massive scale of the physical quantities we're working with.
But listen, even if you know the units and the shorthand, it's still so easy to fall into the vault security traps. Ordinary revision fails because it only focuses on the equations, not the actual execution. Look at the most common traps examiners report year after year. Missing units on a final answer, rounding numbers way too early in a multi-step calculation, giving these vague, wordy explanations instead of tight scientific ones, mixing up variables, and oh man, messing up the scales on graph axes. Just memorizing the textbook is not going to cut it. You have to use mark scheme thinking to dodge these exact traps.
Let's actually see this in action with a quick comparison. On the left, we've got a seriously flawed answer. The student's calculator spit out 12.33333, and they just wrote the whole thing down. No unit, totally unrealistic precision. Why is it unrealistic? Because the calculator has absolutely no idea that the distance was measured with a standard school meter rule, which only has millimeter precision. That gets 0 marks for the final output. Now on the right, look at the top-end answer. It filters the raw math through reality, 12.3 meters. It has the correct significant figures reflecting the actual measuring instrument and the proper SI unit. So that's your first quick win. Never, ever write down exactly what your calculator says without filtering it through reality first.
Now, securing the marks for numbers and units is really just phase one. There's actually a hidden directional clue that changes a resultant calculation completely. It's a trap that literally trips up thousands of students. In a moment, I'll show you exactly what that directional clue is, but first you need a framework that makes that clue totally obvious.
So here is your master key. This is the perfect answer framework for any complex calculation or explanation in Physics 0625. Step 1. State the concept. Identify the physics principle right out of the date. Step 2. Extract the evidence or data. Pull the relevant numbers and units straight from the question. Step 3. Apply scientific reasoning. Show your substituted values inside the correct equation. And step 4, use examiner wording. Wrap the whole thing up using the exact terminology the mark scheme demands. For example, state the concept. Okay, this is a kinetic energy problem. Extract the evidence. The mass is 2 kilograms. Apply scientific reasoning. Plug it into half mv squared. And use examiner wording to conclude. If you do this, you literally leave them no choice but to award full marks.
All right, let's apply that framework to the concept I promised you earlier, the absolutely crucial difference between scalars and vectors. This right here is that hidden directional clue. See, many physical quantities just have a size, a magnitude. We call those scalars, like mass or time. But vectors have both magnitude and direction. Think about speed versus velocity. Speed is just how fast something is going. That's a scalar. Velocity is how fast it's going and in what specific direction. And honestly, if we miss the direction, we've missed the entire concept of the vector.
So why does this matter so much for the mark scheme? Because when you're combining two vectors, let's say two forces acting on an object to find the resultant, you cannot simply add the numbers together. If a 3 Newton force pushes north and a 4 Newton force pushes east, the resultant is not 7 newtons. Because they are perpendicular vectors, we have to account for direction using a scale diagram or Pythagoras' theorem. Do that and it reveals the true resultant is actually 5 newtons. The direction dictates the path, and the path dictates the resultant size.
And just like we have to be super precise with direction, we've got to be highly critical of our measurement reliability. Let's escalate this to a practical data scenario. Any single measurement you take, like timing a single pendulum swing, is just not going to be entirely accurate. There's always going to be an error margin associated with human reaction time. A single measurement equals a high error margin. But if you take the average of several measurements or measure multiples, like timing 10 swings instead of just one, you drastically reduce the size of that error and massively increase your reliability.
Okay, let's put this mark scheme thinking to the test. Check out this statement. The time interval is 0.4567 seconds. I want you to mentally pause for a second and predict the error here based on what we've just been talking about with measurement techniques. Think about the devices you actually use in a simple school physics lab. Can you spot the error?
Well, if you caught it, great job. The crucial point is this. There is no standard school stopwatch that can accurately measure down to a 10,000th of a second, mostly because human reaction time, just starting and stopping the watch, introduces an error of about 0.1 to 0.2 seconds anyway. So writing out 4 decimal places shows a complete disconnect from practical reality. The examiner correction here is crystal clear. Always check your final answer for reasonable significant figures. Your conclusions must be strictly supported by the practical data limits. If your human-operated stopwatch realistically only measures to 1 or 2 decimal places, your data absolutely needs to reflect that reality.
So, you've got the master key now. We've cracked the vault on numbers, units, significant figures, and that really critical distinction between scalars and vectors. We know how to structure a perfect answer and reduce measurement errors. But guys, the heist isn't over. The examiner has set even deeper booby traps hidden within specific question types. We have the framework, but we still need to know exactly how an explained question differs from a described question. Otherwise, we'll still trigger the alarms and lose those hard-earned marks.
Ask yourself this: if you can flawlessly calculate a vector now, do you know the exact difference between describing its motion and explaining it? Because misunderstanding those command words is the final alarm tripwire. Escaping with the full grade boundary requires knowing those exact traps. So, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations, and click the next explainer on your screen right now to navigate the examiner's deadliest traps by question type. Don't leave those marks behind. I'll see you over there.